Hello everyone and welcome to yet another recreational programming session. How about that? So today we're going to continue working on NN.H, which is a deep learning framework in C that we've been developing for quite some time. You can find the source code of this thing here in the description, right? And today I wanted to focus on something rather interesting. So in the third episode of Machine Learning in C, which you can find in the description, so it's called The Most Important Machine Learning Algorithm, it was brought to my attention that the way I do backpropagation is not particularly traditional. It was brought to my attention by Francis Kim Jonsen. I hope I pronounced your name correctly. Thank you so much for pointing that out. So essentially, if we take a look at like very simple model, right, which is basically a sequence of neurons, right? So we have M neurons and each of them is connected with a certain connection with a certain weight, and each of them have a certain bias, right? And for the sake of simplicity, let's actually say that we're not going to have too much data. Let's say we're going to have like one single sample of data. So we don't have to do the sum and then take an average of it. So there will be no sigma sign and divided by n. So it's going to be super simple, right? So if you use my approach where I defined a sequence of cost functions for each individual layer, you're going to end up with something like this, right? But if you consider a cost function as a single entity and you literally just stank all of the math and compute each individual partial derivative manually, you will end up with something like this. And this is what was pointed out by this specific pull request. Right, so this is pretty much the same thing, except, we do not multiply by 2 on each individual layer. Right, so here we only multiply by 2 the first time for the derivative of the activation of the the last layer, and then we continue just like multiplying by the corresponding derivatives of the current layer, right? So there's no like constant multiplying by 2. And my approach actually results in something very interesting, and it results in the parameters of the first layer being modified too quickly, because as you progress towards the beginning of the neural network, you keep multiplying by 2, so the parameters start to basically change faster and faster and faster. Right, so you can even see that effect in the simulations that we actually implemented, specifically in image.nn, right? So where we train the neural network to act like an image, actually like 2 images, so then we can interpolate between them. Right, so let me actually maybe rebuild this entire thing just in case, so we have a fresh build and stuff like that. There we go. I'm gonna sip my tea while everything is building, and let's actually start the image to NN, and let's provide 2 images that we want to interpolate. Right, so I have a little bit of a MNIST database in here, so we're going to interpolate from 8 towards 6. I'm not sure if you can see everything. I think I forgot to put something behind my camera yet again. I really apologize for that. I should probably put that into my to-do list or checklist of things I do before the stream. So anyway, right, so here is the sort of the simulation, the gym in which we're training neural networks, right? So in here we're training neural network to act like both of these images, and as soon as it learns how to act like both of the images, we're able to interpolate between those images. So it's a very cool animation generator, I would say. Right, so you cannot see the effects of our backpropagation approach in here unless the neural network is deep enough. Let's actually make it a little bit deeper than whatever we have in here. So image to nn.c, and where is the architecture? So here is the architecture. So let's actually make it a little bit deeper. Something like that. I think that's a good architecture for the neural network. And let's maybe rebuild everything like so. I'm gonna rebuild and run simultaneously. All right, looks deep enough. Looks deep enough. Okay, so let's actually let it train for a little bit, and you'll notice something interesting, right? So we'll have to wait a little bit until it just like kicks in. If it doesn't kick in for too long, maybe we'll probably reduce the the depth of the neural network, but I think it should kick in any minute now. Any minute now? It's having a hard time kicking in, so maybe we should reduce the amount of layers. Let's remove one layer. Okay, sure. The neural network is too deep for this entire thing to learn, and we're using sigma activation function, so maybe we have a vanishing gradient stuff. You know, thing may happen. So this is machine learning. In machine learning, you never know what can go wrong. So to fix things, you just need to, yeah, there we go. You can clearly see, look at that. Look at what's going on. Like only the layers towards the beginning are being modified like crazy, but as you go towards the end, nothing really changes at all. And like you can clearly see because we color this entire stuff. Right, and as you can see, these things are just flickering and going crazy. And this is the result of our approach of that extra 2 that we add on each iteration on each layer, right? So if we restart, you will see that again. So just to confirm that it's not a fluke or fluke, how do you say that? I don't know. So, and yeah, if we try to use a traditional approach now, right? If we try to use a traditional approach now, it's going to be a completely different picture. Right, so let's go to nn.h, right, so the header specifically, and then backprop. All right, and so basically what we have to change in here. So according to this thing, so the first thing, the first partial derivative has to be multiplied by 2. So this thing should be multiplied by 2, like so. And the things that were multiplied by 2 should be multiplied by 1 now. So this is a very simple change, right? So I was very close, I think. So I hope I didn't actually make more mistakes in here, and I interpreted the pull request correctly. So I think this is what we have to do in here. If I misinterpret the pull request, please let me know in the comments. All right, so I'm going to restart this entire thing. And we'll see how it goes. Right. So it is doing something, but now it is not really learning anything. Right. And it can go like that for quite some time. But this doesn't mean that this approach is wrong, right? So if we reduce the depths of the of this entire neural network, right? So if we go back to what we had before, this entire approach is going to work actually, right? So let's actually remove it like this, and let's restart it. So this is the traditional approach. There we go. So, and as you can see, it is learning, right? But you may probably notice that it's learning a little bit slower. It's kind of difficult to compare. I think we need to have some sort of a mechanism that will allow us to flip-flop between traditional and non-traditional approaches. So let's actually do a little bit of modification of the source code. Right, so I want to introduce some sort of a macro, and let's call it nn backprop traditional. Right, so let's call it traditional, and basically if this macro is defined, we're going to use traditional approach, and if it's not defined, we're going to use non-traditional approach, right? So and then backprop, let me find the function. So here is nn backprop, right? And if we are in nn backprop traditional, right, we're going to be doing this thing. Otherwise we're going to be doing the thing without multiplying by 2. Right, so essentially it's going to be just like this, and in here we're going to have and if. There we go. So, and in here we just have to switch between this, sort of like a factor. One of the things I'm thinking is that I can introduce a variable called s, right, and I can define it some way here, right? So, and essentially if we are in a traditional mode, it's going to be just 1, otherwise it's going to be 2. Right, it's going to be essentially 2, and let's do and if, like so, right? So right now we are in traditional approach, hopefully. Okay, so notice the length of this thing before it actually starts to go down and learn anything. Right, so it's quite a long thing. If now we're switching to non-traditional approach that we had before, right, it's gonna actually learn faster, right? It's gonna learn faster. You can clearly see that. It learns faster, but at the same time, it's crazy. Look how crazy it becomes when it like finds something in here, right? By this point, I actually want to reduce the rate to sort of calm it down. And this craziness kind of helps this entire approach, non-traditional approach, to penetrate like a deeper neural networks, right? So if we have deeper neural networks, this sort of added craziness, right, it allows it to penetrate all of these layers and learn at least something. I don't think it's not particularly good way of training the neural network because it doesn't like utilize like further parameters in here, right? It only focuses on these parameters, but at least it just starts doing something, right? Whereas with such depth of neural network, if you switch to a traditional approach, it's incapable of penetrating that at all. Right. So even though our non-traditional approach is actually crazier, right? It's way crazier, but it's suitable for like training like a deeper neural networks, especially the ones that use sigmoids, right? So I don't know, like I wouldn't rule out this approach completely. Right. So this kind of situation left me confused a little bit. And as far as I know, the creator of this pull request actually, yeah, so they actually share this sentiment. Basically, they said that I'm hesitant to make the corresponding changes to the actual source code because when I run the test, the conventional approach actually seemed to worsen the performance. Yeah, for this specific setup, for this specific neural network with sigmoids and stuff like that, this, you know, additional multiply by 2 on each layer kind of helps to like drive the cost function down a little bit faster. And this is the thing about machine learning, right? So the method of training the neural network does not have to be mathematically correct, whatever that means, right? So it has to be something that just drives the cost function down, right? Whatever you can come up with that drives the cost function down, it works, right? So and that's the main goal anyway. Right. So what's interesting is that this only works with that specific activation function, right? And sigmoid activation function is very like, you know, how to say that, safe, in the sense that like whatever crazy values you throw at it, they're still gonna end up in the range of between 0 and 1, right? It cannot go super crazy. It kind of limits itself, if that makes any sense. So our non-traditional approach with constant multiplication by 2 may not work with other activation functions that are not as limiting as a sigmoid. And this is something that I would like to explore on today's session, right? So let's just have this, you know, switch between traditional and non-traditional approach and see how it performs on different activation functions, right? And this is an opportunity to explore some other activation function, as you can see. So it cannot just penetrate this entire thing. Even though this is like the traditional correct sort of approach, it still cannot do that. Anyway, so let's actually introduce a couple of more activation functions and see how they react to our training process, right? So I think it's going to be interesting. So as already mentioned, we use sigmoid activation function. So we have a function sig, right, which applies sigmoid to the matrix. And the other very popular activation function is called ReLU, right? So let's actually Google it up, ReLU. So it's a rectifier neural network. So what's cool about this function is that it's super simple, actually. So essentially, so it accepts input x, and if x is greater than 0, it just returns x without any modifications, and if it's less or equal than 0, it returns 0. Right, so it has a shape of sort of these things, as you can see, just straight up. Like if it's below 0, it's just like a straight line in here. If it's above 0, it's just like the same line in here. So, and the derivative of this function is also pretty straightforward. If x is greater than 0, it's the derivative is 1. If it's less than 0, it's equal to 0. It's not defined at 0, but usually people just straight up ignore that and they pick like arbitrary value. They pick basically value either 0 or 1 at x equals 0, right? So you just pick 1 and it kind of works usually. So let's go ahead and implement that. So we have a sigmoid. Maybe what I want to introduce, ReLU f, right? So usually in CF denotes that we're working with floats as opposite to doubles. Right, so let's actually do float x, sigmoid f, right? And essentially if x is right, less or equal than 0, we want to return 0, otherwise we want to return x. So this is how we can implement that. There is another interesting way of implementing this entire thing. So essentially if x is greater than 0, if you take this Boolean value and reinterpret it as float, it's going to be basically 1. So essentially you can just say, okay, multiplied by x, right? So in that case, if this thing is true, this entire expression is going to be x, right? This entire expression is going to be x, and if it's false, it's going to be 0. Actually, I'm not 10% sure. So well, I mean, yeah, so essentially this thing is going to be integer 1. It's probably going to be converted to float, and it's going to be 1. So this entire thing is going to work out correctly, but I actually want to double check that. Right, so let's super quickly double check this entire thing. So I'm gonna just iterate maybe float starting from -1 up until 1, and we're gonna just plus 0, 1, right? I think that's a reasonable thing to do. And let's just do f to f, and it's gonna be x, ReLU x, and let's just try to run it and see what's gonna happen. All right, so what do we have? This one's interesting. So it's -0. Okay, I mean it's still 0, but it's -0. But if it's above, it's the same thing. Okay, it seems to be working. All right, so what we need to do now in matsig, we have to actually apply ReLU, but that kind of means that we probably want to change the name of this function because it's not going to be about sigmoid anymore. In fact, I think it would be better to call this thing something like matact. So instead of like applying specifically sigmoid, we're going to be activating that function, right? I think that makes a little bit more sense. I hope you agree with me. So, and in here, let's just apply ReLU. But that's not enough, right? Because in the backprop, right, we are also computing the derivative of the activation function, right? So, and the derivative of its sigmoid is a sigmoid multiplied by 1 minus that sigmoid, right? So this value is the derivative of sigmoid, right? So, and I would like to maybe factor it out to a separate variable like this. That was actually kind of weird, but anyway. So something like this. So it's going to be separate variable q. And essentially, since we're using ReLU now, what I can do, right? So basically, if a is greater or equal than 0, we're going to be returning 1. Otherwise, it's going to be 0. To be fair, we can just like do something like this. And of course here it's not a, it's q, right? So that's basically the derivative that we can pick in here. So, and let's give it a try and let's see if it's going to work or not. So now we're not using sigmoid, hopefully, we're using the ReLU. And the problem with the ReLU is that I never could actually make it work. So as you can see, it sort of, jams this entire thing and the cost function becomes none, right? So since ReLU is sort of like very much unbounded on the plus side, you don't really want to use this like huge of a rate of learning. So you probably want to actually reduce it like very, very low, something like this. And even with such a rate, it still kind of like goes like, oh, did you see that? It was actually, yeah, so this is actually pretty cool. Yeah, I really like that. So, and yeah, it doesn't really do anything. So let's actually make it super, super small. Oh, it's doing something. It is doing something, but it's going crazy. And I wonder what kind of approach do we use? I think we're using traditional approach, right? Yeah, it's, well, at least it found something resembling 8. Right, it found something resembling 8. And here's an interesting thing. Look how blocky everything is. Look how blocky everything is. So I'm going to actually make a screenshot. And if you look at it, it's not particularly as smooth as the sigmoid. If you take a look at the sigmoid, it was actually very like ghosty and smooth and stuff like that. I wonder if we can just switch quickly between these things. I think we need to introduce a similar mechanism that allows us to switch between activation functions, if you know what I mean. Right, so it would be nice to have something like, I don't know. Let me see. So maybe we could define something and then act. And here we could specify like what kind of activation function do we want to have. Like maybe we're going to introduce something like enumeration. So this is going to be activation, and we can have activation function, which is a sigmoid or the ReLU, right? So, and in here I could specify something like act sigmoid, right? And everything related to the activation is going to use a sigmoid and stuff like that. So mat act. Right, and in here we probably want to do something like switch and then act. Right, so to be fair, it probably better if it was like some sort of a runtime value. Right, so act. So let's go to the signature in here. So act. Let's go back. And here we're going to do switch upon act. So case act sig. Right, so and in here this is how we are activating this entire thing. So this is the break, and then here we have act ReLU, right? So this is ReLU, and this is break. And if we encountered something that we didn't see before, we're gonna, I don't know, throw some sort of like an exception. We don't have exceptions in C, but you know what I mean, like unreachable. There we go. So this is basically what we can have in here. Hopefully the compiler is smart enough that it will basically put these, you know, loops inside out, right? It's not going to do a switch on each individual iteration. I hope at least in 2023 the compilers are smart enough to not do that. But you never know. But who cares? I mean, in 2023 you have powerful computers. Okay. So this is what we have, and we also need to modify the derivative in the backprop, right? So here, where do we compute derivative? So here is the derivative. And the backprop, do I want to pass this entire thing to backprop? Probably not. So let's actually do switch case. Switch and then act. All right, so this is going to be case, act. Of course, basically, this is actually a very important disclaimer. This is not how it's going to end up being, right? So obviously, I want to have a much nicer like interface for like choosing activation functions and stuff like that. The only reason I do this like sort of hackish thing is because I want to quickly introduce new activation function without refactoring too much. It's just like doing that properly and making it so pretty and stuff like that just requires too much refactoring that I don't want to do on a recreational programming session because I'm exploring things, right? So what I'm doing, I'm just exploring and just want to see like how different activation functions affect different things, right? So that's why it is what it is and it isn't what it isn't. So maybe I want to define this thing in here. So then later I can do something like this. Right, so this is going to be like that, and this is ReLU. There we go. So let's remove that. So this is going to break, and by default in here, we're going to say something like nn assert, and I'm going to say unreachable. Right, so this is unreachable. Cool. Okay, maybe because of that, since I already sort of like switch on a compile time value, maybe I'm not gonna accept additional thing in here, right? Because I already do that anyway. So who cares? And then act, and let's not pass this entire thing in here. All right. So hopefully that will make it easier to then add more activation functions. so we can play with them and see how they go. Right, I think that's a very useful thing. So yeah, all right, so this is a sigmoid, right? So this is a sigmoid, and what kind of training approach we're using? I think we're using traditional one, which is not going to work, so we want to use a non-traditional one. Right, so let's rebuild this one more time, because traditional one is incapable of penetrating this many sigmoid layers. Right, let's use a non-traditional one. Okay, hopefully it will start penetrated very soon. There we go, it penetrated stuff. So it's going too crazy in my opinion, so let's reduce its craziness. And if we save the screenshot, so right now it is saving screenshot, right? So if we take a look at the screenshot, it is actually very smooth. Look how smooth it is. It's very smooth. Let's actually do sigmoid, right? So let's actually rename this entire file, so because we want to save it, and let's go back to a different activation function. Let's go back to ReLU. Let's go back to ReLU. And for ReLU, we actually want to make the this thing very, very small. And even, yeah, there we go, right. If we take a look at the results of this activation function, they're not that smooth. They're very much blocky, right. So let's actually save this thing. So it's still saving the screenshot. Yeah, there we go. So as you can see, it looks like a polygon. It's still gradientish, but you can see these clear lines. You can see these clear lines as with sigmoid, right. So where's the... Yeah, there's no such clear, like, sort of edges. That's what I was looking for, not lines, but edges. Right, so we can even compare them, maybe. Is it possible? Probably not. Thank you, Emacs. Right, so you can see these clear edges, and it looks like constructed out of polygons, whereas this thing is actually super smooth and feels like constructed out of these curves, like Bezier curves or something like that. And this is basically different activation functions. And why activation functions actually have such a profound effect on the final result of the neural networks? This is because the neural networks actually use activation functions as building blocks of the function they're trying to interpolate. Right. So essentially, like, each neuron is basically one piece that the neural network can use to stitch together the actual thing you're trying to train it to behave like. And in case of a sigmoid is a very smooth thing. It's going to consist of like these smooth curves. And in case of a ReLU, which is just like this, like, angle, right, like angle thingy, is going to try to stitch together like different lines and try to construct out of that. And that's why this thing is super blocky. Right, so there's a very cool video that I found on the internet about that. So the video is called Why Neural Networks Can Learn Almost Anything, I think by Emergent Garden. Right, so I'm going to leave the link in the description in here. And they explain how the neural network actually approximate those like the different functions that you're trying to train them to behave as, right, and depending on the activation function, they're gonna basically have like different shapes and stuff like that, right? So it's actually very cool. Anyway, right, so unfortunately ReLU doesn't really work as well as I would like it to work, right? It's just doing something, but having a hard time to learning anything. So what people usually suggest, and what people suggested to me on Twitch, is just like try to use Leaky ReLU. And Leaky ReLU basically doesn't, like, never makes the negative part of the function super flat, like in classical ReLU. What it essentially does, let's actually go here, nm.h. mat-act, where is mat-act? So maybe I probably want to go to here, to this ReLU F. Where is the implementation? Right. So essentially what it does, right, it multiplies x by this small parameter. Right. So it's not going to be super flat. It's going to be like very steep. Is that a good word to use in here? But yeah, so essentially, I think even on Wikipedia, there is a description of a leaky function. I hope there is some sort of like a plotting of this thing. Probably not. We can actually draw that. All right. So let me just draw the axis. So here are the axes, X and Y, and so essentially the classical ReLU is going to look like this, right? So it's super flat, but Leaky ReLU is going to look like this, and the negative part is going to be sort of like this, right? So essentially, the value of the function still affects the input parameter of the function still affects the value of the function on the negative side, but not as much on the positive side, right? And that is more flexible, I suppose, and it actually helps the neural networks learn a bit faster and easier, right? So let's actually try to use a Leaky ReLU and see if Leaky one will actually learn anything. Right, so we modified the value in here. We can actually take this parameter and move it sort of like to a separate macro, and then ReLU program, right? Put it somewhere here. Define and then ReLU param. So in here, and essentially, if you want a classical ReLU, just set it to 0. Right, so it's actually super easy. So it's more general that way. Right, and regarding the derivative and the backprop, let's see what we have to do in here. So where is the derivative? Okay, so in case of that, this is going to be 1, otherwise it's going to be an n ReLU param. Okay, so that one will allow it to learn a little bit more precisely, hopefully. A little bit more precisely. Okay, there we go. So, and of course, we still need to make it learn a little bit slower. And all right, and it's actually learning. Look at that. So, and it actually like looks like, yeah, it looks like the shape of these things, right? It actually does look like that. What's interesting is that what approach do we use? What approach do we use? I think we're using a traditional one. Look at that. With the traditional approach, we're actually able to penetrate like all of these layers super quickly if we just use the ReLU activation function, specifically Leaky ReLU, because non-Leaky one like never works for me for some reason, right? Maybe because like the neurons dies out super quickly, but this one actually kind of does something. But you can see that the background is kind of weird, right? So, and this is a bug of the rendering, right? So let's actually take a look. So there's a bug of the rendering. Where do we render the previews? Preview. Somewhere here. So here are the 3 previews. So essentially what we do, we take the output activation of the neural network and multiply it by 255 and assign it to 8 pixels. This would work if the activation function is sigmoid that keeps the activation between 0 and 1. So that means it will never be less than 0 and greater than 255. In case of a ReLU or Leaky ReLU, this thing can be way over 1, so it overflows. And because of that, the background actually kind of weird, right? I think background literally underflows, right? So, and that's why it's super white. What we probably want to do, we want to put this entire thing into some sort of like activation, like in here, right? And we want to clamp it, right? So if it's less than 0, it's going to be 0. If it's greater than 1, it has to be 1, right? And only then we want to multiply it like this, right? So that's basically what we want to do in here, right? That's basically what we're going to do. And let's actually go through all of the previews and just like replace things like this. There we go. And let's recompile this entire thing, and that should fix the rendering, hopefully. That should fix the rendering. All right. Oh, yeah, sure. Just a second. I need to make it small by default. Is it learning? Okay, so it is learning. Look at that. So it is doing things. All right, and we can try to interpolate between these images, and that's actually kind of cool. It scrolls between them. Since it is so linear, instead of actually like morphing different curves and stuff like that, it just scrolls between them. Like, why not? You can just scroll between them. We can even try to maybe render this entire thing, right? And we'll just actually see how it looks like. Yeah, it looks super blocky. Like it can consist of these like ReLU blocks and stuff like that. And it looks nothing like the sigmoid one. The sigmoid one is actually super smooth. Right, but no matter what kind of activation function you choose, you still interpolating some other function. It's just like you're interpolating it with different chunks, right? Maybe with curved chunks, or maybe with like a straight chunks or whatever, right? So it's still interpolation, but just with different pieces. And it managed to learn the thing. And does it still scroll? It does, in fact, still scroll. It's actually pretty cool. That's super cool. And that is with a deep, well, it's relatively deep. As far as I know, people make even deeper neural network. And this is with deep neural network and traditional approach. So traditional approach with a sigmoid couldn't penetrate this neural network, but with the ReLU, it does penetrate this entire neural network. But what if we use a non-traditional one, right? So what if we use a non-traditional one? So let me actually see. Right, a ReLU, but non-traditional one, the one that we came up with on the third episode of this entire thing. So is it going to also penetrate or maybe even learn faster? We'll see, we'll see. Okay, so of course it's too fast. Let's reduce the training. Okay. It's still able to do that, but it's way more crazy. Yeah, it's too crazy. Even though we set the learning rate smaller, it is still a little bit too crazy, right? So essentially, I guess this non-traditional approach is very useful when you have deep neural networks with a sigmoid activation function, because they allow you to like penetrate like deeper and deeper and just like drive this entire thing faster. But as soon as they reach some local minimum, they get too crazy and too difficult to control. So I'm not sure if you want to use that non-traditional approach standalone. Maybe with a combination of other approaches, it might be useful, like just like as initial learning breakthrough, just like quickly drive somewhere and then switch to a traditional one to like refine this entire thing. So that could have been actually rather useful, right? But as you can see, it's too crazy, right? It's too crazy. And I suppose this non-traditional approach with this additional like two coefficients on each individual layer, it acts more like elevated learning rate, probably, but I'm not a specialist in machine learning and stuff like that, so I don't really know. You know what's interesting? It actually learned. This is a ReLU, right? So it managed to interpolate ReLU quite well, right? It's ReLU, right? So let me double check. It's not the sigmoid. Yeah, it is ReLU. I wonder how it's going to look like if we try to render a video out of that, because we recently implemented like a video. How it's going to look like? I'm really actually curious. So I'm going to start the video. And I think, oh, it's going to actually do that very slowly. Yeah. So this is because we are doing full HD rendering. We're doing full HD. Yeah, this is full HD. So one of the things I want to do probably is do something smaller, right? We can do 412 and 512, and let's restart this entire thing. That's actually pretty cool. All right. Okay. So gonna make very small learning rate, and let's try to learn something. So it is learning. Well, it's just going. All right, it's doing things. Okay, let's just let it cook. Let's just let it cook. So I really want to see the moment when, yeah, so here it scrolls. Okay, let's actually try to make it interpolate, but, you know, in terms of like scrolling, because I think scrolling is actually kind of cool. I want to see how it looks like with like 60 FPS and like in higher resolution. So here's its rendering. So we're feeding the frames into FFmpeg. All right, and FFmpeg should create the video for us. So the progress is actually this thing. As soon as A becomes 1, it means 100%. So we managed to render 100% of the video. We're just doing animation and stuff like that. Okay, yeah. So maybe I'm gonna cut at this point, so I don't know what to say right now. So okay, so it's finished rendering, and let's take a look at the final video. I'm gonna use MPV, and let's see. Okay, so this is how it looks like. So it's basically trying to scroll between two scuffed numbers. Right, so, and this is because of a different activation function, right? That's actually super cool. All right, so yeah, what if we try to use like more shallow neural network, if you know what I mean, the original one, but with ReLU activation function, right? So let's actually see. Right, so let's use traditional approach, right, because it's more controllable in case of using ReLU, and let's go ahead and do that. All right, so let's reduce this thing. Let's make it more small. All right, so it is learning something. Okay, it's very blocky though. Is it going to make another breakthrough at some point? I really hope so. I'm hoping for a breakthrough. Maybe there will be. Okay, so it's going down. Going down. Is it gonna make something? I feel like it doesn't have enough elements to construct the things out of. Right. Maybe we should give it more neurons in the layers. Right. What about just making it 28? Right. So 28, 28. All right, so that's very interesting picture in here. That looks rather cool, I think. All right. Yo, what the fuck? It's actually going crazy. Okay, set it to too small, I think. All right, is it gonna learn to behave like the numbers? Hopefully, because I want to see something. This actually looks cool. All right, it's learning. Like on average, at least it's going down, right? It might feel like it's stuck, but on average, it's slowly going down. That means at some point it may perform some sort of like a jump, like a breakthrough. Hopefully, I don't know. I'm just coping, I suppose. Right, but it kind of stopped on average. Right, okay, let's give it another try. All right, so as you can see, sometimes it just does these breakthroughs. Looks like something out of horror, right? A little bit. Okay, so 6 kind of resembles the 6. Hopefully, it will. Okay, so it's going somewhere. It's going somewhere. We just need to like let it cook for a little bit. It's a pretty cool transformation. Pretty cool transformation. Okay. All right. So, yeah, you get the point. So it's not the only activation functions that we actually have. So one of the other very popular activation function, as far as I know, is called Tanh, and it's another sort of like smooth activation function. It's a hyperbolic function. Okay. We can try to add support for this function as well, right? So let's take a look at the definition of this entire thing, and it's rather straightforward, right? So we can pick maybe this definition, right? So this definition looks pretty easy to implement. Right, and what kind of shape does it have? So 10H is, oh yeah, okay, so it's the one which is blue and dotted, right? Which is blue and dotted, and it kind of looks like a sigmoid, right? It kind of resembles the sigmoid, but it's slightly different shape. Right, it's actually from -1 to 1. In case of a sigmoid is from 0 to 1, and this one is from -1 to 1. So that means it will be able to output negative values if we ever need this thing to do that, right? So we can give it a try. And I think derivative, if I remember correctly, is also pretty straightforward, right? So Tanh derivative, right? So what's the derivative? Okay, I'm pretty sure Google should be able to just tell us what's the derivative. Oh, it's basically 1 minus square of Tanh. So that means we only need the value of this function. We don't really need x for this function, which makes it super easy to integrate into our current system without too much refactoring. So I'm actually super happy about that. So let's go ahead and try to introduce the Tanh and see how it performs. Right, so this is a Tanh. All right, so and let's find and then act. All right, so case act Tanh. So this is when we're activating the matrix. So maybe we'll have to introduce a function for that, Tanh-f. I'm not sure if C already have this function, and if C does already have that function, I suppose it's gonna, complain about that. Right, ReLU Tanh F, and let's find the implementation of ReLU. So what's the value of this function? So we essentially have these two values, like e to the power of x and e to the power of minus x, which probably means that we may want to have like separate variables in here. So this is x and then yanks, right? So it's basically negative. Right, so this is a negative one. And essentially what we do, we take the difference between x and yanks, right, and divide it by the sum of these things, right, so x plus yanks. And that's basically what we want to have in here, right? So this is the value of the function. So what about the derivative? What about the derivative? What about the derivative? Okay, H. So if I remember correctly, it was 1, actually 1 minus a multiplied by a, right? So yeah, it's this one. So that's basically the derivative. Okay, so let's give it a try. So now we are using ReLU. Let's make it use Tanh, right? So I don't know if Tanh is even used, right? So what I hear these days, people use either ReLU or sigmoid. The other thing people use these days is also GeLU, right? So it's like another hot thing in machine learning, which is like ReLU but smooth, right? So the thing about ReLU is actually it's very like angular, right? So but GeLU is like ReLU but smoother. It doesn't have this like very sharp edge or anything like that. So we may add it at some point, right? So we may add it at some point. I forgot the break. So this is the reason why I put asserts in here. This is literally the reason, right? Just in case I forget the break or something like that. Let me double check if I didn't forget the break on the other side in here. No, I didn't. Okay, so that's cool. That is very, very cool. That is very, very cool. All right, so I suppose the final result here is going to be, okay, so you also probably need a very small learning rate for that specific, okay, right, very small learning rate, so it is learning, but maybe a little bit faster. Maybe we should let it learn a little bit faster. Is it going to do something? Well, it is learning. It is actually learning, which is kind of cool. So though it's kind of different, especially in the background, right? It is still smooth, but at the same time, yo, this is actually kind of cool. What the fuck? I wanna see this shit in higher resolution. Okay, so let me actually render the upscale version. Right, so let's take a look. Let's take a look at killed. Yeah, it kind of looks like a sigmoid, but the transition is actually different. It's not a sigmoidish transition. It's actually, this is actually way cooler. I really like that. Look at that. So let's let it cook for a little bit more, right? So I want the to drive the cost function a little bit more down, because 6 is kind of meh in my opinion, right? So let's take a look at 6. It's kind of close, right? But maybe if we let it, you know, cook for a little bit, it's going to be even better. So it's actually kind of cool how trainable it is, right? It's kind of cool how trainable it is. And the approach we're using is a traditional one. Yeah, it is a traditional. Right, and with the traditional approach and the hyperbolic function, it works really well, right? So maybe we also want to take a look at non-traditional one. Let me actually quickly render the video, right? Because I want to see how the transition just looks like in case of a video. And of course, it probably going to take some time, so let's quickly cut it. All right, so it finished rendering, and let's take a look at the transition. So the low resolution transition should look like this. I really like how there is sort of like the whoosh effect throughout the entire sort of screen. I really want to see that in a high resolution. Right, so I'm going to use MPV, and let's loop it as well. That's actually super cool. And I suppose the whoosh effect throughout the entire screen comes from this like long things that goes towards infinity from left to right. But I mean, sigmoid is kind of similar to that as well, right? I don't know, right? It's kind of cool to see like different results depending on the activation function, right? So, and yeah, it's, you can literally see the effects of activation function and why it is important, right? And so maybe depending on how exactly you want to interpolate the final result, you may just make different decisions on the activation function, right? Maybe you don't want to have the sharp edges, and because of that you may not want to use ReLU, right, for whatever reason, right? But the cool thing about ReLU is that it's super simple, right? It's like one comparison. It's literally one comparison, and if it's parametric ReLU, it's actually also one multiplication. In case of sigmoid, it's just like it's power to the epsilon, right? So there's also then division, and the same goes for the hyperbolic function and stuff like that. So it's like they're more costly, right? The cool thing about ReLU is that it's super cheap computationally, right? It's extremely cheap computationally because it's just comparison and multiplication, and that's it. One comparison, one multiplication, right? So for faster learning, I think it's a little bit better, right? So, but we were using a traditional approach to training the hyperbolic function, right? So let me see. What about the non-traditional one, right? Is it going to go crazy? It's probably going to go crazy, right? So because you have like just faster learning for the left, for the layers that are closer to the input. Let's call them like that, right? So, and this one is just like kind of jammed. So let's actually put the learning rate somewhere here, and it's not that crazy, right? I wouldn't say it's that crazy. So we're using the non-traditional approach. Yeah, we're using a non-traditional approach. And this is because the neural network is not super deep, right? So it's not super deep. Let's actually make it a little bit deeper and see, right, if it's gonna go super crazy, right? Okay, deep neural network, deep, relatively deep, and non-traditional approach. So this thing should start going crazy, right? According to my understanding of how all of that works, right? So let's actually make it super small. It doesn't really go that crazy. It actually goes fine and learns super fast. Okay, so this is a non-traditional one. This is such a cool look at this transition. What the fuck? Look at this transition. Holy shit! I've never seen such transition before. Yo. I want to render that. Okay, I'm gonna quickly render that, right? So I just want to see that at higher resolution. All right, so it's done, and let's take a look at this beautiful, beautiful transition. This is the most awesome transition I've ever actually come up with. This is so cool. It's just like this arm detaches and attaches again. So the 8 is kind of scuffed, but this is so cool. Yeah, I'm sure. Yeah, it's probably due to the different activation function, but this is so cool. Okay. Right, I need to save that. So I'm gonna call it cool. Right. So, all right. So what do we have here? We have a deep neural network, and we have a non-traditional activation function, right? And it learns relatively fast, I would say. It learns relatively fast, right? Probably due to like sort of increased learning rate, right? So what about a traditional one with hyperbolic function and deep neural network, right? So let's actually see. So the traditional should be a little bit slower. Does it mean that the non-traditional approach actually kind of helps for this kind of neural network to learn faster? Actually, yeah, I'd say it's a bit slower. It's learning a bit slower. It's more like, you know, calm, I would say, but it's a bit slower. So, okay. So rough conclusion is that the non-traditional approach with like faster learning rate kind of helps on these like very smooth functions that squash the activation between like 0 and 1 and -1 and 1, right? So especially on the like deeper neural networks, because they actually help to penetrate this entire stuff faster. Right, but on ReLU, such non-traditional approach is just too crazy, right? Because ReLU is unbounded, unsquashed, so it just like goes too crazy, and you probably want to use traditional approach there, probably. So non-traditional one, look how quickly and beautifully it learned, like very precisely as well. Right, but again, it utilized only the things that are closer to the input. It's kind of, these things are kind of underutilized, but maybe that's what you would expect for this kind of like problem. I don't know. Somebody needs to actually research this kind of thing, I think. Maybe. I don't really know if it's worth researching, right? But I kind of find this thing rather interesting, right? So it's like less precise. It's a little bit crazy, but it just finds something very, very fast, especially if you have a lot of like layers and stuff like that. And as far as I know, like I remember hearing that there is like a problem with vanishing gradient on deeper neural networks with sigmoid. Does that help with that? Maybe, I don't know. I'm not a machine learning person, so I need an adult to actually educate me on all of that, right? So I don't really know what the fuck I'm doing, right? That's for sure. I'm just playing with different things, with different activation functions and stuff like that, and sharing my discoveries, but I'm not a scientist or mathematician or anything like that. The hyperbolic one actually kind of cool. This transition is cool. Yo, the Tanh comes up with way cooler transitions than sigmoid, in my opinion. Look at that. Or maybe I'm imagining that. I don't know. Right. So this one is actually kind of cool. So there is another interesting activation function that I heard almost nobody uses. Like I heard almost nobody uses that activation function, and that is a sign activation function, right? So, and the problem with sign is just it's kind of funky, right? So it doesn't really necessarily squash, right? If the value gets too big, it may drop from 1 to -1, right? And it keeps like oscillating and stuff like that. But people say that you can like train very interesting neural networks with a sign activation function. So let's actually add a sign activation function and see if it does any good. If it does any good. So let's switch back to traditional approach. Right, so let's introduce sign, because why not, right? We're just experimenting, right? We're just farting around, So let's go to mat act, right? Mat act, and introduce the sign activation function, right? So in here we're going to be just using synth, right? So, but there are some problems with derivative of such function, right? I think there are some problems with derivative of such function because, yeah, we only know the value of the function, right? So we set up all of the things so we know only the value, and if you can't compute the derivative by the value of the function, we can't really integrate this entire thing. So we can still add such feature in here, but it will require a lot of refactoring, which is kind of outside of the scope of today's session, so I don't really want to do that. Right, so what's the derivative of sine? I think it's straight up cosine. Derivative of sine. It is cosine, right? So, and to compute the cosine of x, I need to know x, but I don't know x, I know only sine x. Maybe I can use arcsine or something like that, right? So, but to be fair, one of the things we can do actually, we can just say arct sine and something like unsupported, right? And then when we're using this activation function when we're using this activation function, we can essentially just use finite differences, right? So instead of backpropagation, we can use finite differences, and finite differences are really interesting because they don't require a derivative. They're actually approximating the derivative by wiggling around the parameters of the model, right? So we can try to do that. But it's going to be super slow on such big neural networks that we're already working with. But we can try to do that on smaller neural networks. So the reason why I wanted to look into the sine activation functions, and this was, by the way, suggested in the comments of I think, a second video or maybe first video in the series. I really forgot who suggested that. But essentially, with the sine activation function, you can solve the XOR problem, the XOR neural network, with one neuron. Right, so we recently discussed that with one neuron it's impossible to solve the XOR-gate because essentially the values of this function, right, they are not linearly divisible super easily. But because sine is such a funky function, you can solve XOR XOR problem with just one neuron, but with the sine activation function. And this is what I want you to try, right? So let's actually give it a try. So since it's such a small neural network, we can just replace the backprop with the finite differences, right? So let's just replace finite differences back, right? Finite differences require an epsilon. Let's set epsilon to like 1,000 or something like that. Right. So yeah. So let's actually make one neuron. So essentially this ends up being one neuron, two inputs and one output. And right, so in the library itself, we are using, let's use sine. Okay, so let's rebuild everything. And instead of running image to an n, we're gonna do XOR. Let's see how it's gonna go. It's kind of interesting actually. All right. So that's free. It learned instantly. The fuck? Wait a second. Yeah, it just learned it. It just freaking learned it apparently. Right. So I would like to know the parameters of the. It was too quick. I didn't even expect that. Like what the fuck. All right. So can we just add additional key in here? Right. So for instance, if is key pressed key S, let's say, we can try to print the neural network that we're currently training. Right, can we do something like that? That would be interesting, I think. Right, just to see the parameters, just to confirm what the hell is going on. Right. Okay. Okay, sometimes it gets stuck, but sometimes it just finds just the right configuration, and here it is. This one is interesting. So, all right. So essentially what you're telling me is that as you can see, the bias is straight up 0, right? Or something very close to 0. It is something very close to 0. If you just take x multiplied by 157 plus y multiplied by 150, let's go 57 as well, because if you round it up, okay, 157, 157. So this acts like XOR. Basically, that's what you're telling me, because this is what we found apparently. Okay, so let me see. I'm gonna start, Python. I'm gonna import math. Right, import math, and we can. Do we have XOR? XOR is not a function, so let's actually define XOR, which is gonna be xy, and let's simply just return this entire thing in here. I want to copy paste this entire stuff, please. So this is sine. Can I do math sine? Okay, XOR 0, 0. Okay, 1, very close to 1. Very close to 1, 1, 0. Okay, so as you can see, it is possible to, you know, come up with a XOR neural network that consists of one single neuron if you use a very special activation function, a sine activation function. That's actually kind of cool. I didn't expect that. That was too easy. What the fuck? All right, so that's why activation functions are really important, right? That's why they're important. So sine is so funky, right? It is so funky that it can solve XOR with just a single neuron. That's freaking amazing. All right, so that's basically everything I want you to explore today, right? So I want you to explore this like non-traditional approach to backpropagation that we accidentally came up with. And I just want to see how different activation functions affect that approach. Right, but at the end of the day, in machine learning, right, so if you came up with something that drives the cost function down, that works, right? So it's not about being mathematically correct. I even heard something, I think on Twitter, that machine learning is not really about math or computer science. Machine learning is more like biology. You're not really building this system, you're just like growing them, like plants, right? And essentially what you do, you just like drive different fertilizers, right? So some fertilizers work better, some humidity, temperature work better, right? So it's not about mathematical correctness, it's just about driving the cost function down. It's about growing the plant, the goddamn plant that interpolates the function, right? So yeah, it would be interesting to know the opinion of like people who actually do professionally, like, you know, neural networks and machine learning and stuff like that, like why this works and is it even useful, right? What's interesting is that we ended up with a very weird approach, right, where we just do extra multiplication by 2 on each individual layer in here, right, which is not particularly necessary. But does it really have to be by 2? What if we make this thing, I don't know, half, right? That would be interesting. So we can take a look at this thing. Right, so I'm gonna go back to the sigmoid activation function, right? So, and we're gonna use non-traditional approach, sigmoid non-traditional approach. And let's actually do the image stuff. So the usual thing that we had before today's session, right? So that's basically what we have. And this thing should penetrate the layers of these neural networks relatively quickly. I think, hopefully, it will. Yeah, there we go. It started to penetrate like around here. Okay, and then it goes too crazy. We can just calm it down a little bit. Maybe it will learn something at some point. Yeah, it's doing something. So what if instead of 2, right, s equal 2, I'm going to put half in here. Is it going to be more calm? Right? Maybe. I don't know. Let's just stir the pile of linear algebra around one more time. Just stir it around. Okay. So, well, it's just doing thing. I can expect that what it's going to do is just like it's going to drop, but much further, much later. Okay. So it's still not dropping. But is it going to drop at some point? Oh, it is going to drop, right? So it just basically, that parameter delayed the moment until it actually started to learn something. But it's a little bit more calm, as you can see. It's a little bit more calm. That's actually kind of cool. All right. It's still learning. It's completely freaking incorrect in terms of like actual partial derivatives or anything like that, but it's still learning. It still drives the cost function down. Okay, what if we say it's going to be 3? What if it's not 2? What if it's 3? Like even crazier than that. Right. Is it going to learn super fast, but then it's going to go all over the place? Right. I don't know. Let's give it a try. Okay. It's not doing anything. It's going even up. Okay, multiplying by 3 was a mistake. It's just like it had some stroke in here, and it's just like it doesn't learn anything. Look at that. Yeah, it fails to learn. 2 seems to be like a magic number for this specific thing, right? So 2 is actually kind of perfect. I don't know. It's kind of weird. Okay. And it starts learning and it goes to crazy. It's kind of funny how it just like goes all over the place. It's just the images have the stroke, having a stroke. It's doing something. Okay. That's a pretty cool interpolation. That's a pretty cool interpolation. So yeah, anyway, so I guess that's everything I wanted to check today, right? So I wanted to take a look at some other activation functions, right? And I think having support for different activation functions is going to be very useful in the future. So one of the things I heard people say is that quite often people use different activation functions on separate different layers. And this is something that I would like our framework to support at some point as well. But that will require refactoring some things. So I'm thinking to introduce some sort of like maybe notion of the layer, right? Maybe some sort of a notion of the layer. Right, so if you take a look at the neural network, so right now, neural network is just like a collection of like weights matrices and bias matrices and activation matrices and stuff like that, nothing particularly special. We could have introduced something like a layer, right? So a single layer which consists of a single weight matrix and a single bias matrix. Right, so and the sizes of the weight matrix define the amount of inputs and outputs of the layer, and here we could store the activation of that specific layer. Why not? And then we can say that the neural network is actually not a collection of those things, but it's a collection of layers, right? So we can put ls in here, and the count is the amount of layers in here, right? And so that will allow you to stack together like different layers with different activation. And maybe in the future, when we start supporting like more different kinds of layers, we can have a like literally kind in here, maybe layer kind. And one of the kinds is going to be just like a fully connected layer, right? So fully connected. So in num layer kind, right? LK fully connected, fully. And another one is could be something like a convolutional, right? Convolutional. I don't know. I never actually like developed convolutional neural networks, so I don't know really how to organize all of that. But I hope to learn that as soon as I start doing that, right? But that's roughly the idea that I want to have, right? So I want to basically have like different layers with different activations, and maybe in the future even different kinds, right? So that will allow us like stack together different layers of these things, because with the convolutional neural networks is just like first you have a bunch of convolutions that sort of filter out like noise and reduce the amount of information, and then at the back end of that neural network you have a fully connected one that makes a logical decision on the perceived information by the convolution layer or something like that. Quite often people use only convolutional layers. I don't really know. So, but for the convolutional neural network, we're going to have a separate stream, and I definitely want to have support for these kind of things. All right, so that's basically everything that I wanted to explore today. Thank you so much yet again, Franz Kim Yonsei. I really hope I pronounced your name correctly. For this pull request and for letting me know that I'm not following the traditions of machine learning. I really apologize for that. I'm not a machine learning person. I'm just, you know, screwing around. Thank you so much. But yeah, that was interesting actually. And yeah, it's kind of cool to see how different activation functions like affect the result, right? So they're not just something that you slap on top of the neural network. It's something that you may want to carefully choose. But I'm not sure if I'm at that level yet where I can confidently say that, okay, for that specific problem, we want to use ReLU. For that one, we want to use hyperbolic one. Like, I don't know, like I don't have enough experience, but I'm getting there. I'm getting there. So yeah, that's it for today. Thanks everyone who's watching right now. Really appreciate that. Have a good one, and I see you all on the next recreational programming session.